All right. Hello, everyone, and welcome to this seminar on building the AI infrastructure for next generation AI architectures. So today we are going to dive deep on the future of AI infrastructure and how this emerging AI architecture is shaping the future of AI infrastructure. So this is the agenda for today. So we're gonna quickly go through some of these trending theme that we see in the world of AI. Then we will cover some of these emerging AI architecture post-transformer. And then based on those architecture, we're going to talk about the scenarios of future AI infrastructure, and then we conclude the session with some key takeaways. All right, let's start the session by this reality check that might surprise you. So when we talk about AI costs, we are often thinking about the wrong thing. So most people focus on training cost, which is the massive compute bill to create the model in the first place. But here is what the data actually shows us. So between 80 to 90% of an AI system total lifetime cost comes from inference. That's actually the day-to-day running of the model to answer a question and also generate response. So to put this in perspective, imagine you spend $78 million to build a factory, but then it costs you $2.3 billion just to keep it running over its lifetime. That's the reality we are facing with today's frontier models. So these numbers actually just completely flip out our infrastructure strategy on its head. So instead of obsessing over how fast we can train model, which is more like a kind of optimizing how quickly we can build a factory, we need to focus on making each individual prediction or text generation as cheap and energy efficient as possible. And that's the difference between sprint speed and also marathon. So you can see this key theme that we are seeing, and the costing and the pricing model is actually shifting from OPEX to CAPEX for AI system. So now also let's talk about why our current AI architecture is hitting a brick wall. You probably heard about transformers, so which is like the classic AI architecture behind all these frontier model like ChatGPT. So there's a problem with this classic AI architecture, and that's what we call it as a quadratic complexity. So you can think of the quadratic complexity for transformer with this analogy. So if the model processing 100 words can cost $1, then processing 200 words doesn't cost you $2. It's actually just $4. And then the same for 400 words, that's going to be $16. And you can see how quickly this gets out of hand when you want to process an entire document or have long conversation. But there's also a even bigger issue here as well. We built all our specialized AI chips, which are expensive, to be really, really good at one thing, which is dense matrix multiplication. And that's actually the base of our all kind of like hardware, like GPUs or even like all these ASICs technology provided by different technology company. And this hardware specialization is creating a chicken and egg problem that's about to become a major headache for the entire AI industry. All right, now let's talk about some of these emerging AI architecture post-transformer. So there are three main emerging model families. So we have the state space model, which is SSMs. We have diffusion models, and also spiking neural network. Let's quickly touch on these three main emerging models. Start with the state space model, or SSMs, which represent a major shift in how we handle sequence modeling. The key idea is that the SSMs approximate continuous time dynamic system. Basically, they give us a way to model very long range dependencies in data without the computational cost that usually comes with it. So at the heart of SSM is something called the selective scan operation. What makes it so powerful is that it can be implemented with the prefix sum algorithm, which is highly parallelizable, and this is actually just what give SSMs the efficiency. Now there are two main ways SSMs operate: in recurring mode, which process one step at a time, and is ideal for inference because it only takes constant time per step, and also in convolutional mode, which you can parallelize the entire sequence at once, which makes training extremely fast and also scalable. Together, this model makes SSMs both efficient and also versatile. So when it comes to the computational requirement of SSMs, they're actually quite different from traditional transformer models. So instead of being limited by raw compute, SSMs actually is memory bandwidth bound. This means the bottleneck is how quickly data can move in and out of memory rather than how many floating point operation you can perform. So because of this, SSMs benefit from having large on-chip memory and also a specialized kernel design to keep state vector highly accessible. During long sequence inference, you need frequent and also fast access to these state vectors, which is where SRAM for retention and also rapid HBM access come into play. Another key point is that the SSMs rely much more on efficient prefix sum acceleration than on dense matrix multiplication, which dominate transformer workloads. As a result, we are seeing remarkable efficiency gain. Like as an example, Mambo 3 billion can match the performance of transformers that are twice its size. That actually shows how promising SSMs are for scaling up with fewer computational resources. Now let's talk about the diffusion model. Diffusion model have become some of the most powerful generative tools we have today. The way they work is through iterative denoising, starting from pure noise and gradually refining it into high quality data, step by step. This makes them excellent at generating realistic image, audio, and other modalities. However, while training this model is computationally intensive, it's actually inference that dominates the lifetime cost, as we covered like at the beginning of the session. So each generation requires millions of small prediction steps, which adds up quickly in terms of compute and energy. This is why optimizing the inference part is very important. Techniques like 4-bit quantization and also dynamic activation sparsity make a huge difference here. So together, they've been shown to deliver nearly 7x speed up and also cut energy usage by more than half, around like 51.5% reduction. These kinds of improvement are critical if we want to scale diffusion model in a sustainable and also efficient way. One of the key challenges with diffusion model is handling dynamic sparsity. Unlike static sparsity, where the same weight or activation can be pruned consistently, here the sparsity actually changes over time as the denoising process unfolds. This means that at each time step, the pattern of active and inactive computation can look completely different. To deal with this, we need a specialized solution, a time step aware sparsity detector. Its role to identify at each stage of denoising which computation can be skipped so that the system is not wasting cycle on zero activation. Without this detection, the potential efficiency gain from sparsity simply cannot be realized. Finally, the hardware itself has to be designed to support this dynamic sparsity. We need dynamic sparsity in genes that can adapt in real time. Without hardware-level support, the software optimizations can only go so far, and we won't see the full benefit of sparsity in practice. Now let's talk about the third emerging AI architecture, which is spiking neural network, or SNS, which represent a radical shift in how we think about computation. So instead of continuous synchronized processing like in traditional deep learning, SNNs operate in an event-driven way. Computation only happens when a neuron fires a spark, and if there is no spark, there is essentially no energy consumption. This approach offers incredible potential for energy saving, often by order of magnitudes, making SNNs especially attractive for edge workloads where power efficiency is critical. Imagine devices like sensors, wearable, or autonomous systems that need to run complex AI model on a very limited energy budget. SNNs are a natural fit for these use cases. What makes these networks even more interesting is their integration of memory and compute within the same crossbar structure. This blurs the traditional separation between storage and processing, and further reduce energy overhead by keeping everything tightly coupled. Together, these properties make SNNs one of the most promising directions for ultra-efficient AI infrastructure. But of course, SNNs also comes with challenges. So while SNNs hold great promises, there are still some significant system-level challenges holding them back. One of the biggest issue is resource mapping. Because computation happens within crossbar structure, networks need to be carefully partitioned into clusters that fit these hardware resources. That requires very specialized computational techniques, not something off-the-shelf tools can handle yet. This leads to the second barrier, the toolchain. Right now, we don't have robust, standardized, high-level compiler support for SNNs. That means deploying them at a scale is still difficult, and most real-world use cases remains limited to niche or experimental application. And finally, analyzing performance for SNNs is not straightforward. To properly model execution, researchers rely on frameworks like synchronous data flow, graphs, and max plus algebra. This provides insight into timing and resource utilization, but they add another layer of complexity that makes widespread adoption harder. So this slide brings together the computational primitive across different model families. So transformers are built around dense matrix multiplication. They demand extremely high throughput, which makes them a natural fit for GPU with tensor cores. State space models, by contrast, rely on perfect sum as their core operation. The critical requirement here is efficient state retention, so a specialized scan engine are the best hardware match for them. Diffusion models lean heavily on sparse convolutions. Because activation patterns change dynamically during the inference, they need fast sparsity detector to skip unnecessary work and also deliver efficiency. Finally, SNNs take a completely different approach. Computation is driven by spark events. Their strength lies in integrating memory and compute directly, and they pair best with crossbar arrays. Together, this comparison shows how each model family is shaped by a different primitive, and why customized hardware is essential for unlocking their full potential. So one of the biggest challenge in modern AI hardware is the memory wall, the gap between how fast we can compute and how fast we can move data. Compute Express Link, or CXL, is designed to address this problem. In its 3.1 version, it provides a unifying memory fabric, allowing tiered and also disaggregated memory pools to be shared across devices. This is especially important for memory band architecture like SSMs, which rely on fast access to large state vector, and for environments with heterogeneous hardware. With CXL, accelerator can pull from the same memory pool instead of being constrained by the memory soldered directly onto them. Without CXL, every specialized accelerator has to operate with its own isolated memory. That not only lead to standard resources, but also to significant inefficiency in utilization. By contrast, CXL enables true memory sharing, which is essential if we want a scalable, flexible AI system. What makes CXL especially powerful is that it does not just expand memory. It actually enables true heterogeneous across hardware. First, it allows dynamic allocation. This means resources can be directed to whichever computational primitive is active, whether it's a transformer running dense matmals or an SSM relying on prefix sums without wasting memory elsewhere. Second, CXL provides memory pooling. With a shared coherent memory fabric, multiple devices can access the same pool seamlessly. No more duplication, no more standard memory sitting idle on one accelerator while another is starved. Finally, CXL support orchestration. It gives us a way to unify the management of different type of hardware. So GPU, scan engines, sparsity detector, or crossbar arrays can all work together efficiently as part of the one coordinated system. Now let's talk about another technology that can shape the future of AI infrastructure, which is photonic computing integration. Unlike traditional electronic processor, photonic systems use light for computation, which gives them ultra high bandwidth and also extremely low power consumption. This makes them particularly well suited for the linear operation which is the heart of SSMs and other recurrent model. What's more, photonic devices naturally operated at relatively low bit precision. Far from being a limitation, this actually aligns well with today's mixed precision inference strategies, where we intentionally trade precision for speed and efficiency. The direct payoff here is clear. For core workloads that require massive linear transformer and extremely high data movement, photonic computing could deliver both the bandwidth and also the energy efficiency that electronic-only systems struggle to achieve. Now let's talk about the software stack. So our software stack here is what makes all the hardware capabilities actually work in practice. We handle dynamic activation sparsity by intelligently skipping unnecessary computation. This is especially powerful for diffusion model that we already talked, and also spiking neural network where lots of activation are naturally zero. Our automated tools figure out the optimal precision for each layer, so you get maximum power saving without sacrificing accuracy. Plus, we automatically recognize when operation can be fused together into optimized kernel, which means we are using every bit of on-chip memory and compute resources efficiently. And here is the key economic shift happening in AI. Your operating expenses now scale directly with how much inference you are running, not just your initial training cost. This means that the game has completely changed from trying to max out your training cluster utilization to obsessing over every penny you spend per query. So the companies that win will be the ones who can drive down the marginal cost through smart efficiency techniques. Sustainability. So the architectures you choose has huge implication for energy consumption. So SNNs are game changer for edge computing because they only activate when there is an actual event to process, which can cut energy use dramatically. State space model helps us avoid the exponential energy blow-up you get with transformer on really long sequences. We are also getting smart about when we run compute jobs Our carbon-aware schedules looks at the local grid data and automatically shift heavy workload to times when the power grid is running on cleaner energy resources. In terms of cloud versus edge, there is a hard latency wall that determines whether you can use cloud or need edge deployment. For autonomous system and industrial control, you need that 95 percentile latency under 50 millisecond, and there's just no negotiating on that. Ultra low power spiking neural network are perfect for this because they can do real-time processing right where the action is happening. Once you factor in network overhead, centralized cloud processing simply cannot hit these strict timing requirements. So edge become your only option. So you can imagine, like for edge use cases, and especially for those that you need ultra kind of latency, so you can use kind of like architecture like SNNs that can provide those capabilities. Federated learning. So federated learning is not just nice to have anymore. It's becoming mandatory in sectors with sensitive data and strict residency rules. The beauty is you can train models collaboratively without ever moving that sensitive user data to a central location, and you still get competitive performance. We are using the Fed DPM framework to tackle one of the biggest challenges when different participants have very different types of data. It uses generative technique to approximate what the global data distribution will look like, which helps the model work well for everyone. So state space model bring real advantage to federated learning because of their linear complexity. You are dealing with much smaller model updates compared to those massive transformer checkpoint, which means less data flying around the network. But we are still working through some tricky system challenges, especially around synchronization that recurrent state across all the different nodes in a decentralized network have. It's not unsolvable, but it requires some careful engineering to get that one right. So what we are seeing for the future of AI infrastructure, there are like 3 key scenarios. And in this section, let's talk about these 3 main scenarios. The first scenario, which is hardware divergence path. In this scenario, we hit a breakthrough where specialized ASICs deliver massive performance per watt gain, especially for those sparse non-dense operation that general hardware struggle with. The supply chain fragments completely. Every model type get its own optimized chip. Co-design become the norm, where your AI researcher are literally telling the hardware team what transistor they need. Data centers transform from rows of identical servers into these heterogeneous pool of specialized chip, all connected through CXL fabrics that can dynamically allocate the right hardware for each workload. Scenario 2, which is software optimization. In this world, software become the greater equalizer. Generic hardware win because we get incredibly smart about the sparsity, mixed precision, and all these novel operators without needing custom chips. All the venture capital and also talent flow into software stack and tooling instead of silicon fabs. Your total cost of ownership drops because you are squeezing every bit of performance out of standard hardware through better utilization and aggressive model comparison techniques. It's basically the triumph of clever code over custom silicon. And then the third scenario, this is where geopolitics and also climate concerns completely reshape the AI industry. Every country start building their own AI infrastructure with domestic supply chain and also these design AI growth zones for deployment. Investment gets spread around based on local factors, where the grid is cleanest, where supply chains are most secure, where regulation are friendliest, and the trade-off is we might give up some global efficiency, but we gain operational resilience and compliance with whether local requirement each region throws at us. So in terms of investment roadmap, there are like three main waves. In the next 2 years, that we will see more pilot on CXL memory pooling to break the memory wall, deploying high efficiency inference GPUs and proving out spiking neural network on edge device can work. In 3 to 5 years time frame, we go big, designing custom ASICs for state space model and diffusion, scaling up edge and federated learning infrastructure, and building the unified runtime that can manage all these different architectures. Long term, we can talk about the really transformative stuff: mass deployment of photonic computing, transitioning to those sub-N compute zone, and also hitting net zero for model training. For researcher, first, we desperately need to understand the scaling law for post-transformer architecture. How do SSMs, diffusion models, and neuro-symbolic approaches actually scale with compute and data? Second, we need bulletproof federated learning algorithms that can handle messy, non-uniform data distribution while keeping communication overhead low, building on what we've learned from Fed DPM framework. Third, we need to benchmark the computational primitive that matter most. The things like parallel scan latency, sparse spike updates, and time step ever denoising that don't get enough attention, but they are actually critical for these new architecture. So for infrastructure engineers, we have 3 critical priorities. CXL integration is non-negotiable. We need these memory pooling pilots running now to handle the massive state requirement of these new SSM workload. We also need to need a proper accelerator abstraction layer that can seamlessly manage mixed precision workload across whatever mix of hardware we are running. No more vendor lock-in. And we cannot ignore photonic computing anymore. We need to assess whether it's ready for prime time and what the real TCO benefit look like for those high bandwidth linear algebra operations that eats up so much of compute budget. For technical leaders, they need to act on 3 fronts immediately. First, pivot your funding strategy. Stop throwing money at training cluster and start optimizing those inference fleets that are burning through your OPEX every day. Second, get strategic about sovereignty. Align with whatever national AI initiatives are happening in your region and make carbon aware operation and supply chain resilience part of your core planning, not at afterthought. Third, establish procurement standards that prioritize flexibility over raw performance. CXL interconnects power efficiency and the ability to adapt as architecture evolves. These are not nice to have anymore. They are actually survival tactics. Also, we need concrete benchmarks for SSM performance, and it's all come down to how fast you can do parallel scan operation. That's the bottleneck that defines everything. We are measuring state update rate in updated per second, plus those critical P95 and P99 latency percentile that matters for real application. The methodology is straightforward. We vary sequence length and hidden state dimension, then Pete optimized CUDA perfect sum implementation against a generic reduction operation, testing both SRAM and also HBM to see where the memory hierarchy breakdown. So now let's quickly also touch on these essential telemetry metrics. So these are the 4 main telemetry metrics that matters most, especially when we are going to do any benchmarking. Performance come down to P95 and P99, latency in millisecond. If you're not familiar with these metrics, check those because these are like very important latency metrics. In terms of the economics, it's going to be cost per 100K inference. The primarily total cost of ownership metrics that the board meeting care about. On sustainability side, track energy per inference for carbon reporting and also regulatory compliance. For system health, monitor CXL pool latency in nanosecond to catch memory access bottlenecks before they kill your performance. All right, now let's quickly touch on some of these key takeaways. So the path forward, moving beyond transforming, is not just about new model. It requires rebuilding our entire infrastructure from the ground up. We need coordinated investment across CXL memory fabric, specialized compiler, and also system that can seamlessly manage heterogeneous hardware that we're seeing. The economics have fundamentally shifted. Optimizing inference is where the money is, not just building bigger training cluster. And increasingly, your architecture decision won't be driven purely by performance metrics, but by sustainability target and also geopolitical sovereignty requirements that are becoming impossible to ignore. Key takeaways, 4 key takeaways to wrap up. We are seeing fundamental architecture shifts from dense matrix multiplication to diverse computational primitives. Parallel scanner, dynamic sparsity, event-driven processor are the new performance driver. The economics have completely flipped. Inference costs now dominant, as we mentioned, 80 to 90% of the total cost of ownership. So infrastructure ROI has to prioritize cost per query over training speed. The technology enablers are clear: CXL 3.1 for memory disaggregation, specialized compiler for these novel operator, and also carbon-aware scheduling. Most importantly, this is not theoretical. You need immediate action on CXL pilots, compiler development funding, and also establishing inference phase metrics across your organization. Awesome. That's all from my side.